So we have the following question. We have two perpendicular straight wires that join in the ends of a semicircular loop with a radius of 17 centimeters. If now we know that the current is 4 amperes, and we want to find the resultant field, magnetic field, at the center of the circular section, so at this blue point here that I've just circled. Now down here I actually have the answer in formula, in a massive formula. Essentially, let's say that your web work is due like in 10 minutes or whatever and you're a bit late. I'd rather you first plug in this formula and just get the answer right, get one more point so that you can at least get a good grade for the web work. The only thing you're gonna have to change in this formula is this value here. Anytime it shows up again, like 0.17, 0.17, yeah. And also the 4 here as well. Basically, wherever I have circled a number, that number is supposed to be changed, because in your problem, represents these three circled values represent the current that I have, which is 4 amperes, but for you it could be 8. So instead of writing 4 for yourself, and it's 8 if it's 8 in your case, write 8. And as for 0.17, that's basically the radius. In my case it's 0.17 meters, but in your case it could be 0.25 meters or whatever, so just plug that in. So that's how you want to plug in this entire formula and just check if it's right. Let's say that it's wrong, you can just follow, I'll explain to you how to do the problem and you can still follow my steps and figure it out. But that's just to save you some time. Now to actually get the problem started, I've taken this diagram, we have this diagram, and I've basically broken it into 3 pieces. Piece number 1, the wire over here. Piece number 2, the wire over here. And these wires, remember that they're no longer infinite because they're curved. They're now curved instead. And then I have piece number 3, which is the semicircle. And I've already done the right hand rule, and I've shaded, I have assigned each specific segment a specific color, and that's basically the magnetic field of this third segment in blue. That's the magnetic field, that thing in orange, of this segment 2 in orange. This is the magnetic field of segment 1 in blue. I'll explain how to use the right hand rule for the semicircle over here to show how we get this, and then I'm sure that you guys can figure out the rest, the other two, using the right hand rule on your own. So I'll assume that I'm standing here, right over here, assuming that I'm on that point. My thumb is assuming now that you have a tablet with you and you're watching this on your tablet. Your tablet is flat on the table. So basically, your table or your tablet is parallel to the y-axis, and the x-axis, it's also parallel to the x, but the x is like pointing towards the right, and the z-axis is pointing out towards the roof or towards the sky, assuming again that your tablet is flat on the table and you're watching this on a tablet. My thumb points in the negative I-hat direction, okay, basically along with the currents. My fingers now, they will start curling above this segment over here, and they're going to curve initially they're going to curve into the page, into the tablet, into the table. And when you keep curling them up until you get a proper fist, on your way back your fingers are going to curl out of the page, out of the tablet, when they get below this segment, this semicircle. So that's how we figure out the magnetic field. Now the reason we're basically below this, we're focusing on the magnetic field at this point here, and to find the magnetic field at that point, we focus below this massive wire. We don't focus up here where the magnetic field is pointing into the page. We focus down here where it's pointed into the page. So we don't care about what's going on up there. So we know that for segment 3 the magnetic field is pointing out of the page towards us or towards the sky. Again, assuming that your tablet is flat on the table. So what I'm saying is, as long as you're inside this massive shape, anywhere in here, the magnetic field from the third segment is always pointing out of the page, out of the tablet. Now, moving on to the wires. You guys can figure out the magnetic field using the right-hand rule or on your own. I'm going to start using the formulas to actually find the magnetic field. I'll start with the wires. So that's the formula for the wires. I'll focus on segment 1, piece number 1. Now I need to find the magnetic field over here at this point. So what do? I draw a line that goes from that point to this segment. This is basically, this point here on the wire is the closest point to that point here, to this point here. Now I know that the angle on the left is 90 and the angle on the right is 90. This is like something like your teacher should have explained to you when starting the chapter, the Biot-Savart law. So both of these angles, theta 1 is equal to 90 degrees, and the angle here, theta 2, is also equal to 90 degrees. To be honest with you, these 45-degree angles here, they're kind of just there to perhaps convey that segment 1 and 2 are like perpendicular to each other, that's all. But if I do the same thing for segment number 2 that I just did for segment 1, again, starting at that point where I need to find the magnetic field and going all the way down to the point that's closest on segment 2, I get the same thing. I get two 90-degree angles. So theta 1 is 90 and theta 2 is 90. So what do we understand here? We know that the current flowing through this entire thing is the same, which is 4 amperes, and we know that the angles for both of these segments are the same. The theta 1 of piece 1 is the same as the theta 1 of piece 2. So we can just solve this equation once and set it equal to the other segment, because we're not going to get a different answer. We're going to get the same answer. So I'll start solving for piece 1 in particular. 4 pi times 10 to the negative 7 Tesla meters per ampere. That's the mu O. That's this thing. Times the current, which is 4 amperes, divided by 4 pi times the radius. The radius is A. It's the same down here. And the radius would be 0.17 meters when I convert it to meters. And now I do sine of theta 1. My theta 1 was 90 degrees, plus sine of theta 2, which is also 90 degrees. Sine of 90 gives us 1, right? So essentially this entire thing becomes 1 plus 1, which means it becomes 2. So when you do 2 divided by 4, I'm just focusing on the numbers for now, 2 over 4, that gives us 1 over 2. Just letting you know that little trick. And I'll try to solve for this. I think this is a good time to mention, we know that the magnetic field from segment 1 is pointing in the positive k direction out of the page, so we'll also write that down. especially because I have the vector here, so I have to show it in vector format, my formula. So that's positive k hat, and I'll plug this into the calculator now, and we'll see what happens. I get a value of 4.71. I'm rounding this answer times 10 to the power negative 6 Tesla, and that's going to be equal to the magnetic field as well of the second segment, because the calculation is the same, everything is the same, so you don't have to repeat this calculation twice. That's what I'm trying to say. Now we focus on that massive semicircle, and we use the formula here. I'll write it down here. So this is the third, I believe, segment, is that right? Yeah. And we know that the magnetic field is pointing out of the page towards us, or towards the sky. So that's positive. 4 pi times 10 to the power negative 7 Tesla meters per ampere times the current, which is 4 amperes, divided by 2 times the radius. The radius is A, and A is 17 centimeters, so it's 0.17 meters when I convert it into meters. And I multiply that by 180 degrees over 360 degrees. So how did we get that angle here? It's very simple. This entire shape is a semicircle. Now let me draw the coordinate axis, the xy plane. Think of a unit circle. The maximum angle a unit circle can form is 360 degrees, right? So when you draw a semicircle, that's going to be half of 360 degrees, which is 180. The maximum angle a semicircle can form is 180 degrees. That's how you figure out this angle. So essentially, let's say you weren't given a semicircle, but you were given the quarter of a circle. It's very simple. You draw the xy. You don't have to do this, but I just drew it anyways. You draw the xy plane, and you draw a quarter of a circle, and you realize that it makes a angle of 90 degrees. That's like the maximum it can make. So then you plug in 90 degrees here, if that was a quarter of a circle. But we had a semicircle, hence 180 degrees is what we are using. So now I'm going to plug these values into my calculator. So I'm going to get positive, that's k hat by the way. Yeah, so I'm going to get 7.39 times 10 to the negative 6 Tesla, and it's in the positive k hat direction. Now hold on, we have to find the net, the resultant, which means the net magnetic field at that point. So what does that mean? That means that I have to add up B1, B2, and B3. Now I'm going to erase some of these calculations to make it easier for me. And I'll make these smaller too. So basically I'm trying to find the net magnetic field. So what I'm solving for is B1, the magnetic field by piece 1, plus the magnetic field by piece 2, plus the magnetic field by piece number 3. So I'm doing 4.71 plus 4.71 times 10 to the negative 6 k hat. So this is just a simple trick I've taught, teacher taught me. If you have the same what's this thing called, exponent, you can just factor it out and it makes your addition so much easier. So I'm doing 4.71 times 10 to the power negative 6 plus 4.71 times 10 to the power negative 6 plus 7.39 times 10 to the power negative 6. So I can factor it out here. And regardless, it's in all of these magnetic fields are in the positive k hat direction. So positive and k hat, like that. This makes your life a lot easier when you're adding numbers. You don't have to include this guy 3 times. So the net magnetic field is going to be, and it's easier to plug this into the calculator. So it's 4.71 plus 4.71 plus 7.39. That's so much easier than having to add an exponent every single time. And that's going to give us 1.68 times 10. Hold on a second. That's actually 4.71, 71, 7.39. That's giving us 16.81. There we go. Times 10 to the power negative 6 Tesla in the positive k hat direction. And that's just a horrible way of writing the vector notation. There we go, that's better. Now I'll plug this into my web work just to make sure it's correct. What a relief, it's actually correct, so that's good. Yeah, so that's how you solve this problem. It's just a matter of, it's similar to the other problems in the sense that you just break a massive shape into smaller segments and use different formulas depending on what the segment looks like. If the segment looks like a semicircle or the quarter of a circle, you use this equation here, and if it's a wire, then you use this equation here, and you just need to be careful with the angles. Generally, with the angles, that's kind of the more troubling part. But anyhow, I hope this video helped. Take care and have an awesome day.